Let's start. Can you see my screen? Hello, can you see the screen?
Yeah,
Okay, yeah. So let's start. First, we'll quickly recall what we saw in this week. So we saw interactive proofs, and interactive proofs for a language L are defined as follows. So an interactive proof is interaction between two parties. One party is called the prover, and another party is called the verifier. An all-powerful prover and a verifier interact, and both of them know a string X. This is the input. The prover's goal is to convince the verifier that X is in the language. The prover, however, need not be truthful. What they do is they interact for k rounds, and in each round, the verifier asks a question AI, or the prover gives a reply AI plus 1 to the verifier's question from the previous round. And at the end of the interaction, the verifier outputs 1 if the interaction has convinced them that X is in L and 0 otherwise. And for like interactive proofs, we have a class IP K. Here K is a natural number. So a language L is said to be in IP K if there exists a probabilistic polynomial time Turing machine V capable of having a K round interaction with any prover P such that the completeness and soundness conditions are satisfied. The completeness condition says that if X is in L, then there exists a prover P such that the probability that V, after interacting with P on input X, outputs 1 is at least 2/3. So this notation over here means that V interacts, this is the output of V after it has interacted with prover P on input X. Similarly, soundness is that if X is not in L, then for all provers P, the probability that V, after interacting with P on input X, outputs 1, that is, it accepts X, is at most 1/3. And the class IP is just the union over all C greater than or equals to 0 of IP n to the C. So in other words, IP is just IP poly n. So these should be square brackets. Will not take these brackets. Yeah. So now in the class IP that we saw, the randomness of the verifier is not visible to the prover. So it's the verified private randomness. Now we can think of private randomness as a verifier tossing coins which are only visible to them. That is private coins. Now we can also think about situations when the coins are public. That is, the prover knows the verifier's randomness. So class AM K is the subset of IPK when the verifier's questions to the prover are restricted to the random strings and the verifier is not allowed to use any other random bits. In other words, it's equivalent. So this definition is equivalent to saying that the prover can see the coins that the verifier tosses to generate its random bits. So basically, in this situation, verifier doesn't hide anything from the prover. It doesn't hide the input X. It doesn't hide the random bits. And uh, so we saw that in the previous slide we saw that IP was the union of overall C greater than or equals to 0 of IP n to the C. However, AM is defined as AM2, and the reason is basically even if you put a higher K over here, you can show that AMK is equal to AM2 for any K. And we also saw two important results. The first one was that IP equals P space, and the second one was that IPK is equals to AMK plus 2. Or oh wait, they should be like contains. Now it's clear that IPK contains A and K, but it's not clear whether IP is contained in like some AM. But what what we can surprisingly show is that IPK is in fact contained in AMK plus 2. So verifier hiding their random bits isn't that much of an advantage. So that's all for recall. So if there are no questions, we can move to the problems. So the first problem is this: an interactive proof system where the verifier is a deterministic Turing machine is denoted by DIP. Which one of the following classes is DIP equal to? The options are P, NP, co-NP, or BPP. So, like, would you like to guess the answer to this one?
Yeah, NP.
Right. Yeah, you might have seen this in class, but let's still see a proof of this. So the proof is divided into two claims. First, let's do this simple direction. Uh, Fix any L in N. There exists a deterministic Turing M which runs in polytime and a polynomial. Let me call it P from N to N such that for all strings X is in L if and only if there exists some Y in 0, comma 1 to the such that this is just a definition of a language being in LP, right? So now consider a verifier. So we want to prove that NP is in DIP. So what we'll do is using this Turing machine and this string, we would construct a verifier and a prover. So consider a verifier V which interacts with any prover for just one round. And in that round, the prover sends a string A in 0, comma 1 to the A. P size of X to P. So what does we do? We just does the following. So we checks if M X comma A is equal to 1. If yes, it outputs 1, and if not, it outputs 0. Now, if X is in L, just consider the prover that sends Y. Okay, so A equals Y. Then VPX, that is V's output after interacting with P on input X. This is just MX comma Y, right? And this is 1. So is this fine?
Yeah.
Yeah. And over here, there is no probability because V is a deterministic machine, right? We are working with
Yes.
DIP, not IP. If, on the other hand, if X is not in N, then for any prover P, PPX. So what is this? This is just MX comma A, right? Where A is the string that the prover sends, but this is 0 for all strings A, right? In 0 comma 1 to the PX, P size of X. So VPX is 0. So we have constructed a verifier, a deterministic verifier, which satisfies both the soundness and the completeness condition, right?
Yeah.
So L is in IP, sorry, DIP. So that this was the like first direction. Now let's look at the second one. So yeah, it's DIP. What do we have? There exists probabilistic polynomial time Turing machine V, uh, polynomial K from N to N such that V interacts, or rather V is capable of interacting with any prover P. Wait, I should type the input first, such that on input X, because the size of the number of rounds would depend on X, that on input X, V is capable of interacting with any prover P for K size of X rounds, and the two conditions are satisfied, completeness and soundness. X is in L implies VP on. Forgot there exists. There exists a prover P such that VP X is equal to 1 and X not in L implies for all provers P, PPX is equal to 0. Again, like there are no probabilities over here because both of like we are dealing with the DIP and so P is deterministic machine. Okay, so now what we'll do is like the opposite of what we did in the for the previous claim. We'll argue that using this verifier and and provers, we can construct a deterministic Turing machine M, which acts as a verifier for NP. Okay, so construct a machine, a deterministic Turing machine M as follows. So M on input X, A1 to AK size of X. So instead of writing the certificate as a single string Y, I'm breaking up that certificate into multiple strings, A1 to AK. Okay, yeah. Instead of writing this as, yeah, let me just write as K. K is equal to size of Kx. This would quicker. Yeah. M on input this does the following. It first checks that A1 is equal to the verifier's output on X, A3 is equal to the verifier's output on X, A1, A2, and so on. A k minus 1 is the verifier's output on X, A1 to A k minus 2, and A k is equal to the verifier's, no, not A k, and if the verifier's output on everything, so the entire interaction is 1. If yes, then M on A1 to AK is equal to 1, otherwise M A1 to AK is 0. Clearly, M is a polytime Turing machine, right? So is this fine? Why M is a polytime Turing machine? Because all of these A1
Yes.
to AK have to be
Yeah.
polytime, right?
Yeah.
Yeah. Okay, now if X is in L, there exists P such that PPX is equal to 1, right? Let A1 to AK, this tuple, okay, so what do I mean by this notation? On the RHS, when I write V and P in angular brackets, I mean that this is this is the interaction of V and P on input X, and A1 to AK equals to the interaction of VP on input X means that the first message was A1, the second message was A2, the third message was A3, and so on. Okay, so let A1 to AK denote the interaction of V and P on input X. Then it's clear that uh, M X A1 to AK is equal to 1. Why? Because, okay, what does M do? It checks that A1 is equal to V1 Vx, which it is by definition. A3 equals to V of X A1 A2, which it again is by definition. AK and so on up till AK minus 1 is equal to V on input X A1 to AK minus 2, which is also true because of the definition of A1 to AK. And finally, because X is in L and P is such that VPX equals 1, this entire thing, P's output on X A1 to AK, so V's output in the entire interaction is also 1, right? So all the checks pass and M outputs 1. On the other hand, if X is not in N, okay, let me do the contrapoint because that's easier. So on the other hand, if there exists a Y is equal to A1 to AK such that M on X comma Y outputs 1. So now what I will show is that this implies that X is in uh, L. So then what we would have shown is that over here we showed that M accepts X if and only if no. So over here we showed that M accepts X if X is in L, and over here if we show that when M accepts X, X is in L, then we would have shown that M accepts X if and only if it is in L, and therefore that M is a verifier for X, right? So let's do this. On the other hand, if Y is this such that M by 1, consider a prover P such that V's interaction with P on input X is A1 to AK, right? Such a prover can be easily constructed, right? All it does is like sort of like you just hardwire A2, A4, A6, and so on into it. So consider this prover. Now, what would this prover do? So it would. So okay. So when V sends A1 to it, it sends back A2. Then V sends A3 to it, it sends back A4, and so on. So basically, at the end, what we would do is we would compute X A1 to AK, which is 1, right? Because of the way we have constructed M.
Yeah.
Yeah. So consider a prover. We said that this equals this. And X is in L if and only if there exists Y in 0, comma 1 to the sum I should write this polynomial before because hence there exists poly P from N to N such that X is in N if and only if N there exists Y in 0, comma 1 to the p size of X such that n X comma Y is equal to 1 and L is in N. And this proves the claim, right?
Yeah.
Yeah, and this polynomial P over here can be derived from K by just multiplying K with the largest, like with the size of the largest sort of A1 to AK string, right? Yeah. So this is related to K, but not exactly K. Now let's move on to the next problem. Yeah. So this is sort of a recall question. So in the setting for interactive proofs, the prover is an all-powerful entity and can always be trusted. True or false?
I think false.
Why?
Because dishonest also.
Right. So if the question were just in the interactives, in the setting of interactive proofs, the prover is an all-powerful entity, then the answer would have been true. But since there is this statement that the prover can also be trusted, it is false because prover can because the goal of the prover is just to convince the verifier that X is in the language, regardless of whether X is in the language or not. So prover is dishonest or can be assumed to be dishonest. So the answer is false. The prover is all powerful but not trustworthy. Next question is also a recall question. So in the setting for interactive proofs, what computational power does the verifier hold? The verifier is a deterministic polynomial time Turing machine. The verifier is a non-deterministic polynomial time Turing machine. The verifier is a BPP machine or the verifier is a p-space machine. So what's the answer to this question?
Verifier is a BPP machine.
Yes, right. Yeah. Okay, so the next problem is consider the class of languages obtained by requiring that there exists a single prover for all x in the completeness condition. Let us call this class IP prime. Which of the following is true? So, is the definition of IP prime clear?
Uh,
Okay, so
mm,
what the
no,
definition
I
is saying
don't.
is the following. In the completeness condition, let me go to the very beginning. So, yeah, so in the completeness condition, there exists the prover. So, what is the completeness condition? X in L implies that exists the prover, right?
Yeah,
However, these provers can be different for different strings X, right?
yeah.
So what that question is saying is that there exists a common prover for all x. So I should write something like this: TMB capable of having a k-round interaction with any prover P and a special prover P prime such that x is in L implies probability Vx P prime x equals 1 is greater than equals to 2, 3. Okay.
Oh, yeah.
So common prover for all strings. The sound of condition remains the same. Just the completeness condition changes. Okay, yeah. So let us call this class IP prime. And which of the following is true? The options are IP is a strict subset of IP prime. IP prime is a strict subset of IP. Both are same and both are disjoint. So like this needs to be proved, but like would you like to venture a guess?
I actually I don't know.
Right, yeah. So it might be tempting to say that IP prime is a subset of IP because okay, in IP prime the condition is stronger, right? There has to be a common prover. So that might it might feel like that sort of reduces the amount of the number of languages that we can accept or decide. But it's in fact the case that both are the same. And let's see why. So first observation is clear, right? This one.
So if the same prover is there for all strings, then it implies that it also satisfy there exists. Uh, in that case, just
Oh right, oh yeah. The
so
other way
all
around,
different
yes.
provers are the same prover.
Okay, so what you're saying is if there exists a common prover, then there
Yeah,
exists prover for everything, right?
yeah, yeah,
And that implies the claim, right? Sorry, the observation.
yeah.
Right. So basically, the completeness condition of IP prime K implies the completeness condition of IP K. The soundness conditions are the same. Right. So the proof is just this.
Yeah.
Now let's do the other direction. Yeah, so yeah, the first thing is just a trivial observation. There is no change in the soundness condition. Uh, Completeness condition for of IPK implies a completeness condition. Yeah, so if we show this, then we would have shown the claim. Now let's show this. So pixel L, what have what does this do? If if L is in IPK, then there exists a deterministic Turing machine which runs in polynomial time. This is just a definition of IPK. So now I am writing the completeness and soundness conditions of IP, right? So there exists. So for in IP, there is a separate prover for every string. So let me write it as PX. Okay. Oh no, now there are probabilities. So yeah. and for all x not in L, for all provers P, probability P. Now consider a prover P such that for all x in 0, comma 1 star, comma, yeah, the interaction of verifier and this prover on input x is the same as the interaction of verifier and prover on x if x is in L and arbitrary otherwise. So, is it clear what this prover P does?
Yeah.
Right. Okay. So, okay. Now I've said that, okay, consider such a prover, but why should such a prover exist in the first place? The reason is the following. P exists because an all powerful Turing machine or functional prover should have no problem computing or finding Px given x, right? Okay, so what does P do? It knows x, right? Now, since it is all powerful, it can figure out what Px is. The special prover Px for the string x, right?
Yeah.
And
Yes.
then it just simulates that.
Yeah.
So whenever V sends an input, so at the beginning it has P as x, it finds out Px. Then V sends input A1, Px would output with A2, and A2 would be the same as the output of P2 on uh, x and A1, and so on, right? So
Yes.
uh, for all x in L, probability at VPx is equal to 1, it's at least two-thirds. And the soundness condition remains unchanged, right? Because the soundness condition is exactly the same, right? Okay, let me write this as P prime to distinguish it from the special prover P. Hence, L is in IP prime. And so IP is contained in IP prime, and we have proved both directions, right? So is this fine?
Yes.
Okay, yeah. Then let's move on to the next problem. So the next problem is as follows. Consider the class of languages for which we have interactive proofs with perfect soundness. So what does this mean? When X is not in L, for all provers, okay, let me write it. So perfect soundness means that for all X not in L and all provers P, probability that this is zero. Okay, now let us call this class IP prime. Which of the following is true? IP prime is equal to P space. I oh this should be IP prime. IP prime equals to BPP. IP prime equals to INP, and both IP and IP prime are disjoint. So which of the these four is true? Like, would you like to guess? I mean, this also needs to be worked out, but still.
Uh,
Okay, first of all, what can we say about IP prime? I mean, can we say that IP and IP prime are disjoint, or can we rule this out?
uh, I don't think.
Okay, so the completeness condition for IP and IP prime are the same, right?
Yeah,
Now notice that the soundness condition of for IP prime implies the soundness condition for IP, right?
yeah,
So IP prime has to be a subset of IP,
yeah.
right? So this option
Yes,
D we can directly rule out, right?
yes,
That leaves us with these three. And all of these sort of can be true because we have seen that IP prime is a subset of IP, but it can as well be IP and therefore P space. And BPP and NP are subsets of P space, so IP prime can be both, right? So far we haven't ruled any of these three out. And that will do when we prove this. But let me first tell you the answer. The answer is that, yeah, IP prime is much weaker than IP. It's in fact just NP. Okay, so let's prove this. The first claim, this should be claim 5. Yeah, the first claim is NP is contained in IP prime. And like, would you like to sort of guess how this is proved? And we have
uh,
seen something like this.
yeah. So we'll consider an arbitrary language in NP,
Right. So
and we'll try
basically
to
this
show that it is
that
in
is
IP prime.
right. So the same as so this proof is exactly the same as the proof of claim 1. Recall that claim 1 was NP is contained in IP. And in fact, if we go back to that proof, what did we do over there? We constructed a deterministic verifier, right? So we constructed a verifier which accepted with probability 1 when X was in the language and rejected with probability 1 when X was not in the language, right? Now I can as well view that deterministic verifier as a randomized verifier, right? So in fact, I get that that verifier satisfies the completeness condition of IP prime, but not only is the probability greater than equals to two-thirds, it's greater than equals to one-third, and the soundness condition is the same, right? Over there it
Yes,
was that it rejects it completely. But if you want to look at that Turing machine as a probabilistic Turing machine, that statement will just become the probability of rejection is 1, right? So this is
yes.
exactly the same proof. So yeah, I'll not do the proof again, but let's look at the proof of the next claim, which is the other direction. This also is similar to the proof of claim 2, but there are some differences. So I'll prove it. Okay, so let's fix any language L in IP prime. Now, what do we have? There exists a deterministic Turing machine P which runs in polytime. Polytime, a polynomial came from such that V on input X is capable interacting with any prover P for K of size X many rounds. And the completeness and soundness condition. Now this is zero because we are dealing with IP prime, not IP. Okay. Uh, so now using this, we'll construct a deterministic Turing machine M, which X is a verifier for NP. So let's do that. Construction is similar. So earlier we just had X A1 to AK. Now we have this extra R. I'll tell you what that is in a minute. So I am on input X, checks, no wait. Let me first tell you what R is. I am on input this, simulates P with R as random bits. So in the first question, we did not need R because we were dealing with DIP. So our verifier was supposed to be a deterministic machine, but now we are dealing with IP prime and the verifier can be randomized, right? So now we need a deterministic Turing machine to simulate a random Turing machine. So we need to give it a string, which it would treat as a random string of V, right? So M on input bits simulates V with R as random bits and checks if V X is equal to A1 P X A1 A2 is equal to A3, so on. V X A1 A K minus 2 is equal to AK minus 1 and V X A1 to AK is equal to 1. If yes, this is not responding properly. Yeah, answer. Oh, what happened? Can't write. Oh, and now it's better. If yes, uh, M X R A1 to AK is equal to 1. Otherwise, M X R A1 to AK is equal to 0. Again, by K over here, I should actually write K of size of X because K is a polynomial. But yeah, again, I'm using the notation and using K as a number. Okay, so yeah, if yes, then this. Is this fine?
Yeah.
So now if X is in L, there exists a random string R, and let me write it like this. There exists, then there exists a prover P such that, oh no, now I can introduce random strings. There exists a prover P, and at least one string R, one random string R, such that when the random bits P R R P P X equals to 1, right? So I've removed the probability by fixing the random bits of P, right? And this
Yeah.
follows from the very definition of IP prime, right?
Yes.
Yeah. So let A1 AK be, so is this fine? Because what does it do? It
Yes.
just performs these checks and all of these would pass by the very definition of this. This is exactly the same argument
Yeah.
as we made in the proof of plane 2. Yeah. Now, conversely, if there exists y in 0, comma 1 to the, let's say, some Pauline size of x such that m x comma y is equal to 1. What I'm doing is I'm just splitting y as r1 to ra1 to ak. Oh, again, I can't write. What's true? This is okay. Let me try to restart the slideshow. I can't even exit. Yes, all of it. Yeah. And why is this? Conversely, if there exists a y, so that mxy equals 1, so y, mxx, x with certificate y, and y I'm just breaking it up as this, then, you know, then let R be the random bits, V, and let P be such that uh, then probability over the random choice of R. So is this okay? What, like, is it clear why this is true?
Yeah.
Because there exists at least one random, like one choice of random bits for which uh, P is able to convince V that X is in L, right? Hence, from the soundness condition, X is not in L, right? This is the same as, yeah, so from the soundness condition, X is not in L, right?
Yeah.
Because what does the soundness condition say? Wait. No. The sound, okay, from the soundness condition, and from the soundness condition, X not in L is not true, right? This is the same as saying X is zero. Why? Because what does the soundness condition say? The probability should be zero. If the probability is one for at least one prover, that means this is false. That means this is false, which means this is false, which means X is in L, right? Put this over here. Okay, now yeah, right, yeah. So, so X is in L. So what have we shown? We have shown that if X is in L, then M accepts, and if M accepts, then X is in L. So M accepts if and only if X is in L. This is the same as the argument at the end of the proof of claim 2. And so uh, L is in NP. Right. Is this fine?
Yes.
Yeah.
Yeah.
So now let's move on to the next problem. Yeah. So given a language A in IP, which of the following is the most accurate statement about A complement? A. A complement is in IP. B. A complement is not in IP. And depending on A complement can be in IP or it may not be in IP. So, like, would you like to guess what's the correct answer?
Actually, that question is not being displayed, so I'm not able to see.
Oh, okay. So, am I not sharing my screen?
No, actually, my network also has a problem, so maybe
Yeah, let
from
me.
my side also it might be a problem.
Oh, can you see the question now?
Yeah, now it
Okay, yeah.
is.
Yes, the question is, given a language A in IP, which of the following is the most accurate statement about A complement? A complement is in IP. A complement is not in IP. And depending on A complement is in IP or A complement is not in IP. So would you like to guess what the
In,
answer is?
I think a complement is in IP
Yes.
because I
Yeah,
think P space is complete. So
right. Yeah, that's the
not
answer.
I mean
Close.
with respect to complementation.
Right, yes. So the answer is this. P space is closed and complementation. Yeah. So now let's move on to the next problem. So over here, GNI is the graph non-isomorphism problem. Okay. So if GNI was shown to be co-NP complete, which of the following statements will be true? P equals NP, P not equals NP, P equals BPP, and pH collapses to sigma 2P. So pH collapses to the second level. So would you like to guess the answer of this question?
Uh, if graph non-isomorphism is co-NP complete, then graph isomorphism will
Right.
be NP complete.
Yes. And then we can just use something we saw in the class. Yeah. Again, I have a problem with that. Okay, yeah, so let me just tell you what the answer is. The answer is pH collapses to the second level. And the reason is the following. If G and I is co-NP complete, then GI is NP complete. Now, in the lecture, we saw that if GI is NP complete, then pH collapses to sigma 2, to the second level. So if G and I is co-NP complete, then pH collapses to the second level. Okay, yeah. So
Yes.
that's all the questions we have for today. If there are no other questions, we can end the meeting. Yeah.
Yeah.
Okay.
Thank you.
Bye.